Thank you very much. So my talk will have group theoretic motivation. It will be mostly about group theory, but subshifts and dynamics will appear soon. So I will talk about everything I will talk about is a joint work with Adrien Le Boudec. So let me start by explaining the words in the title. So I'll take G a group, a discrete group, countable, say, and I'm interested in the space sub G of all subgroups of G. So this is, as you might know, this is you can see it as a compact space if you put on it just the product topology. So you can see it as a subspace of the set of all subset of G with the product topology, and it's compact. And G acts on sub G by conjugation. So what is what I call a confined subgroup of G? H, a subgroup of G, is confined is if, when you look at it as a point in this space for this action, and you look at its G orbit, so if what I'll call, so it's G orbit, which is just the conjugacy class of H. When you close it, let me call this C of H, the closure of its G orbit. So this is a closed closed G invariant subset of the space of all subgroups of G, and I want this to does not contain the trivial subgroup. In other words, you cannot accumulate, so you cannot accumulate H on the trivial subgroup by conjugation using elements of G. Okay, so let me give some background on this notion. So first of all, an equivalent, this you can translate in a much more algebraic way, but maybe less so. More elementary, but less motivated in appearance. So H is confined if and only if you can find a subset, finite subset G are of non-trivial elements of G. So G, but non-trivial, such that all for every G in G, the conjugate of H by G intersects P. So this set's non-trivially. Okay, so this is just because if you translate what it means, like intersecting all finite subset trivially is all finite subset of G minus the anti-trivial is a basis of neighborhoods for the trivial subgroup in the product topology. Okay, so where does this notion come from? So examples. Well, example 0 is if you take H, a non-trivial normal subgroup, just because it's a fixed point for that action. And more generally, well, this is somehow very trivial case. And another example, which is a tightly related notion, and is maybe better known, is if H is a uniformly recurrent subgroup, URS. So it's uniformly recurrent subgroup, which by definition means that the action of G on the closure of the orbit of H, so the CH which is there, is minimal. Okay, this is a notion introduced by Glasner and Weiss. Because, of course, if it's minimal, it cannot contain the trivial subgroup because that's a fixed point, if H is non-trivial. So. And so, indeed, this notion, but that's a bit more general. So, and confined subgroups and URS arise naturally when you look at actions on compact spaces as stabilizers. So let me also give another definition, another example. Assume that G acts on X, a compact space, and then let me say that in such a way that the action is what I like to call topologically nowhere free. I'll explain what it means. So this means, again, by definition, that for every point in X, there exists G, which fixes a neighborhood of X. So not only every point is fixed by some element, but even like as a little bit more in a topological sense. So why this terminology? Typically, one calls an action topologically free if no point satisfies this condition. So if every element, the set of fixed points of every element has empty interior. This is the strong negation of that. And for minimal actions, it is exactly the negation of topologically free. It's equivalent. An action is either topologically free or topologically nowhere free. Then the action of G, then for every X in X. So if you have this property, then for every X, the stabilizer Gx of X, the subgroup of elements that fix X, is a confined subgroup. So whenever you have a summary, whenever you have an action on a compact space which is non-free in a strong sense, its stabilizer must be confined subgroups. This is just an exercise from that definition. See, and for minimal actions, this is equivalent to the fact that the action is just not topologically free. Okay, so with Adrien, we've been studying a lot this notion, and it turns out that studying, so it's not obvious what it is interest, but there are many interests. So something that hasn't been looked at so much until a few years ago, and it's a very natural notion. It arises from topological dynamics, and understanding in a systematic way confined subgroups of various groups has a lot of applications to various different problems. The notion actually, the terminology was coined by Zaleski, Father, and some collaborators in a setting of locally finite groups, pretty far from what I will discuss, in order to study group algebras of locally finite groups. But then there are applications to C-star algebras, to rigidity properties, to groups acting on, to group actions on compact spaces. And today what I want to talk about is a new application of this notion to a group theoretic problem, which is the other half of my title, which is high transitivity. So now break from these confined subgroups, and I will talk about what is high transitivity. So here I will take always G a group, and omega will be just a set, not necessarily a topological space. And a group action is said to be highly transitive I will always abbreviate it by HT if it is transitive of n tuples of distinct points. So writing it out, spelling it out is if for every n tuple of points distinct, which are distinct in omega, and whenever I take another such n tuple, then I can find G in G such that which maps each omega I to the corresponding omega prime I. So in an ordered way. Okay? And for short, I will say that G is a highly transitive group if it admits a faithful highly transitive action. Maybe let me go there. They said yes before, but okay, I'll stick here. Better to not to. Yeah, but it seemed not to. Oh, okay. Okay. And yes, maybe it's better because many. So. Okay, so a remark equivalently, which is a bit more conceptual. G acting on omega is a highly transitive action if and only if so when you have an action, you have a homomorphism to the symmetric group, the group of all permutations of omega, the same thing, if and only if the associated homomorphism has dense image. Where the symmetric group over any set is a topological group with respect to pointwise convergence. Okay, if the set is countable, it's a Polish group. So this is also sort of a nice reinterpretation of the same notion, and you want to naturally know which groups do admit such actions. How do they look like? So it seems that at first sight a very restrictive property, so, but it's not. So let me write some examples.
So Nicolas, let me interrupt you. We have a question
Yes.
on the chat. So by Amir Kodayan, could omega be also finite?
Yes, why not?
So to precise the question, I mean the trivial action of a group on a singleton always works.
Faithful.
Okay.
Yes, but I'm interested. It could be, but I'm interested specifically in infinite groups, and the interesting thing here is that for all n, for n arbitrarily large. That's the point. Okay. And for finite groups, is very well understood actually. Like transitivity degree, you can generally define the transitivity degree of an action as the biggest n that does that. And of groups, and transitivity degrees of finite groups are completely classified, can be completely classified using the classification of finite simple groups. It's really interesting for infinite groups. So, okay. So examples, well, there is sort of a class of somewhat trivial examples, but which is, well, example 0 is the symmetric group over a set is obviously highly transitive group because it acts highly transitively on the set omega, and a slightly smaller group in here, so 0 prime, is the group. So here inside you can look, for instance, at the group of finitely supported permutations. It's still highly transitively. And more generally, for finitely supported, you can define the alternating subgroup of, I write an F here, of finitely supported permutation. Okay? And so this is a normal subgroup in there. And actually, it's contained in every non-trivial normal subgroup. So this group is topologically simple as a topological group, because this is a dense subgroup. And so it means that every closed normal subgroup is equal to the non-trivial is equal to the group itself. And abstractly, every non-trivial normal subgroup contains this guy, which is them. And so 0 prime prime is every G that can be realized which admits an embedding inside the group of sim, which contains, whose image contains alt. Okay, so of course every subgroup of it which contains that is still highly transitive. And why do I call this somewhat trivial examples? Because they're not really trivial, but they're very, very, very well understood somehow, this class of examples. So because so first of all, if G is like that, it contains a normal subgroup which is isomorphic to a finitely alternating group. This is a very restrictive algebraic condition. And so by the way, this is, let me write proposition definition. We say that G is partially finitely, partially finitary if it satisfies one of the following equivalent conditions. So the first one is this one. The second, if G admits there exists a highly transitive faithful action containing G contains an element of finite support. So whenever you have a highly transitive action, it's easy to see that as soon as you have a permutation of finite support in your group, pam, you get all the alternating group. Just because using high transitivity, you have all conjugates of that permutation. So you have a normal subgroup in the symmetric group, right? And 3, I want to write, so the same, except that instead of highly transitive, I can just assume that the action is primitive. So primitive means that it does not preserve a non-trivial partition of omega. This is a theorem, a classical theorem of Jourdain and rediscovered, I think, from the 70s, from the 19th century. So it's a class of groups that we understand very well. And moreover, in this case, the action of G on the set omega that appears is the unique highly transitive action of G. Okay? This is a very classical permutation, like theory of permutation groups, and using these equivalents, you can. It's not so hard to prove this. So when you have a group which, okay, that's the presence of finitely supported permutation in a highly transitive action is somehow a very special condition, and it's sort of a separate world. So I'm interested in studying groups which are highly transitive actions which are not partially finitary. Shouldn't have, well. Okay, so more interesting examples. Non-partially finitary examples of highly transitive groups. So one is non-abelian free groups. This is also not so difficult to see, but so here I have a long list of references. Where is it? Okay, this is due originally to McDonough in the 70s. So this. But from this, you can actually generalize a lot these results. So surface groups also do this. The result of Kritos. And I could continue this list a lot. The point is that surface groups share with free groups the fact to be hyperbolic groups. So this is also true for hyperbolic groups. It was generalized later by Chainikov. And there were a lot of results for groups with hyperbolic properties establishing the existence of a faithful, highly transitive action. And the ultimate result in this setting is due to, so the nth result well, is due to Hull and Ozin, who proved that all acylindrically hyperbolic groups emit actually plenty of highly transitive actions. I won't give the definition of a acylindrically hyperbolic group, but it's just a generalization of the notion of hyperbolic group that covers really a lot of examples, including hyperbolic groups, mapping class groups, and so on. There are more results for groups acting on trees, for instance, due to Pierre Fima, François Lemaitre, Suyung Moon, and Yves Stalder, and for subgroups of SL2, whatever. I will stop here for this list. And there is another source of example, so which is much closer to the topic of this conference.
So Nicolas,
Yeah.
there is another question on the chat by Ville Salo. He said, so sorry, I missed something. What action is highly transitive for these?
No, it's not at all it's not at all obvious how to see. So there is not. So these groups come with a natural action on a hyperbolic space, for instance, but it's not. You don't see the action directly there. It's actually the way this is proven is by some sort of small cancellation theory over hyperbolic spaces. Not really. I mean, but arguments that are so what you want to do is to construct a subgroup H so that the action of G on the coset space of H is highly transitive, and you approximate H successively. I'm actually not super familiar with the proof, by using some methods that resemble a lot the small cancellation theory over geometric versions of small cancellation theory. So it's really not explicit. So and it's not obvious at all why such actions should exist, but they do. So a second class of examples is, which is quite different, is the topological. So if you take a group action minimal, so if you take X to be a Cantor set, and you look at a minimal group action of any group on X, then you can look at the topological full group of the action so let me not write the definition because I won't really use it, but let me say what it is. It's just the group of all homeomorphism of X which locally coincide with elements of G. So this is a very flexible group, and this is highly transitive. So is highly transitive on each of its orbits. Okay, whenever you have in X. Whenever you have an orbit, you have so much flexibility that so here you do see natural highly transitive actions. And a special case of this that will be important for me is the Higman Thompson groups. So let me write it here. VD. So what it is, you take X now to be X indexed by D, the shift space over the one-sided shift space over a D letter alphabet. Okay, so it's a counter set. Now, for a word W in finite word in the finite word in the alphabet. So this is the monoid generated by the alphabet. Let CW be the cylinder set. So the closed set of all sequences that start with W. And you can define a group, very natural group, which is locally given by take a cylinder set, take the W, and change it to another letter. So BD is the group of all homeos G of X such that there exist partitions into cylinders X equal CW1 and X equal C V1 of the same, so the n is the same number of pieces, such that G acts as follows. Whenever it sees an element which belongs to one of the pieces of this partition, so it means which starts with some letter, some word WI, it changes to the corresponding pieces down, word down. So this is the Higman-Thompson group, and it's a special case actually of topological group. Yeah, so, well, let me. So this discussion raises two sorts of problems. So when people study highly transitive group actions, there are not, by now really a lot of results about the existence of such actions, which might be counterintuitive for some groups. Like many groups admit faithful highly transitive actions. But what is missing somehow from this discussion is the following two general problems. OK, we know that highly transitive actions, there are many. Find some structure. So classify the highly transitive faithful. So they're very general problems. It's not a specific question of groups. So beyond proving that they exist, once they exist, one can try to find classification results to understand the structure. And actually, when we started this project, I think the only known result in this spirit is this one that comes from the Jordan theorem from the 19th century. But for in none of these cases there was some understanding of the possible highly transitive actions. And the second problem is there is actually a lack of interesting obstructions to high transitivity. So So there are a few elementary properties. I don't want to get into this. It becomes more algebraic. But one can list a few sort of kind of trivial abstractions, or not so trivial, but not so difficult to for a given group G to admit a highly transitive action. But this is something that is not well understood. So it stays at a very algebraic and elementary level. Maybe I'll tell a bit more about this later. First, I want to get to the actual topic of my talk. So to the actual results I want to state. Okay, here. So remember, I started talking about confined subgroups, so now the result I want to state is a link between the notion of confined subgroups and high transitivity. So which says that essentially when you have a group acting highly transitive somewhere and you have a confined subgroup, the action of the confined subgroup essentially remains highly transitive in the following sense. Let G acting on omega be a non-partially finite. So I want to exclude the case there. Highly transitive action, faithful action. Let H be a confined subgroup of G. In G. Then there exists a cofinite H invariant subset. So with finite complement, such that the action of H on omega 0 is highly transitive. So the action of H remains highly transitive if you admit to discard finitely many points. So this can be useful in both directions, to understand confined subgroups once you have a highly transitive actions, and once you understand confined subgroup of a group, to understand its highly transitive actions. And that's the direction I want to explain. Because the point is that a confined subgroup of a group can be much smaller, much more constrained than the group itself. So the fact to know that the action of a much smaller group remains highly transitive is a strong constraint somehow. So some applications. Two applications. How much time I have? Okay. We started at how much time do I have? We started at 40, 38. Huh?
You have like 10 to 15 minutes.
D'accord. Okay. So first application is related to the classification problem. So it's not an immediate corollary of this theorem, but this theorem can be used as a tool in certain cases to find some classifications. And I'll just state an example, which you can maybe guess by now. So theorem 2 is that every faithful, highly transitive action of the Higman-Thompson group Vd is conjugate to an orbit, is the action on an orbit in the Cantor set. Remember, this is the shift space. So here you see a family of highly transitive actions from its natural actions. Each orbit gives you one. And these are the only ones. So it's not immediate how to deduce this theorem from that, but this is really the main tool. There is some arguing from here to that I don't want to explain now, but let me just say that the point is that here we know that since in the standard action of VD, all stabilizers are confined subgroups, and even stabilizers of finite sets in the Cantor space are confined. So using that theorem, assuming that this is not the case, we managed to show that. So this theorem essentially implies that if this is not the case, then stabilizer of finite set in the Cantor set must act in a highly transitive way on the mysterious highly transitive actions when one is given. So it tells you that their action is very rich. This information you can turn around to say that if you're given an arbitrary highly transitive action of this group, and you look at the stabilizers of n tuples of points for that action, they must act in a very rich way on the Cantor set. Because saying that a subgroup acts highly transitively sort of say that your group decomposes in the product of these two groups. And now, so we can work with the action on the Cantor set. We know that stabilizers must be very large subgroups of V with respect to its action on the Cantor set, and by working, we managed to prove that actually they must be either the stabilizer of a point or the whole thing. So that's how sort of one proceeds. Okay. So now I want to give you at least to state another application that is related to theorem to the other problem, which is also a pretext to advertise a class of groups that might be pertinent to this conference. So I want to explain you how to obtain a class of non-highly transitive groups which do not satisfy any really obvious obstruction to high transitivity, also arising from dynamical systems, like as groups of dynamical origin, I would say. So for this, let me start with, now let's go back to really dynamics. Let me take X phi, a minimal Cantor system. Where X is a Cantor set and phi is just a homeomorphism, so an action of Z. Okay? And I want to define a group that is associated to this system, which is sort of similar to the topological full group of the system, except that I will define a group which acts not on the Cantor set itself, but on the mapping torus of the system, on the suspension space. So for this, let me define y phi to be so the suspension of the system. So the quotient of x times r, where I identify the suspension. Okay. So this is just the mapping torus in the usual sense. Now the idea is to look at groups that act by homeomorphisms on this suspension space. And so for this, let me first just give you so another. I have 5 minutes, right? Yeah, OK. So I will make it. So in order to understand this space, you can think of it. So this space is obviously locally Cantor set times R. And there is a natural system of coordinates, actually, that I want to introduce explicitly to define the groups I want to talk about, which is the following. So let me call them charts. So for C, a Clopin set in the Cantor space, and I, an interval of length smaller than 1. When you look at the product of C times I, it's a subset of the thing that you're quotienting. It injects in the quotient because there is no equivalence relation there. So this you can identify it with a subset that I will denote U C times I of the suspension space. And this identification gives you sort of local coordinates of Cantor set times R in here. So I want to define a group which acts on, by homomorphism on this space by preserving each orbit of the natural lamination of the suspension space, but in coordinates is given by PL, piecewise linear homomorphism of R. So homomorphisms that are piecewise affine, piecewise of the form AX plus B. So definition, and this is a family of groups that we define with Michele Triestino. So I'll note PL phi, the group of all homeos of the suspension space of phi, such that for every point in the suspension space, there exists a chart containing the point and a homeomorphism from I to some other interval, which is piecewise linear, PL, with finitely many breakpoints for the derivative, such that when you look in coordinates G in this chart, so you can, it maps it onto the restriction of G to this chart. It maps it onto the chart defined by C times F of I. And in coordinates, what you see is just the identity times F. So basically, you have these small flow boxes, and your group is acting by elements that act on these flow boxes, like in a piecewise linear manner on the flow direction. And identity means that preserve every leaf, and the jump is locally constant on the Cantor direction. Okay. So these groups we introduced with Michele with a completely different motivation, because they are groups that act, interesting groups that act on the real line. And actually in there, so here I take all possible piecewise linear homomorphism. If you restrict to a countable set of piecewise linear homomorphism, for instance, the so-called dyadic ones, where you ask the slope to be a power of 2 and the constant term to be a dyadic rational, like in Thompson groups, you also get a subgroup of that, which is analogous to the Thompson groups, if you know what it means. And we were interested mostly in that, because we proved that that subgroup is finitely generated when phi is a subshift, simple if phi is minimal. So that gives you, for instance, a family of finitely generated simple groups which act on the real line. And it has other properties. But now I don't want to talk about this. I just want to say that this construction also gives. So theorem 3 that we proved with Adrien is that if you take x phi any minimal Cantor system, and you take G, a subgroup of this group of piecewise linear homomorphism of the suspension flow just defined, which is such that the action of G on the suspension space is what I defined at the beginning, topologically nowhere free, far from being free. So each point is fixed, a neighborhood of each point is fixed by some element. It's large enough. Then G has no faithful highly transitive action. The point, I don't want to get too much into the details, but the point behind this result, it also uses, of course, the main result I stated before, is that under this condition, stabilizers of points of the suspension space are confined subgroup of G. And in this group, the peculiarity of this group is that its stabilizers of points in there look very, very differently from the group itself. The reason is that when you have a minimal lamination like that, if you're fixing a point, and by definition you're also fixing a small transversal, then you can sort of decompose, using the first return map, you can decompose the space into long rectangles, which are preserved by every element in the stabilizer of a point. And so basically this tells you that the stabilizers of points in here look like groups that act by piecewise linear homomorphism on an interval. And this is a much more constrained class of groups because, for instance, I said here there are simple subgroups. They cannot be simple because you have slope at extremes. It's known that they cannot have free subgroups by a result of Breen-Squire. And we actually generalize this result of Breen-Squire as a small generalization to prove that they cannot be highly transitive. So it's along the same lines. And then using the theorem, you can globalize from the stabilizers to the whole group. That's the main idea behind. And I'll stop here.
Thank you, Nicolas. Are there any questions online or here in the room? Yes. Oops. By François Lemaître.
So you mentioned that these Higman groups, right?
Higman Thompson groups, yeah.
They can be viewed as topological full groups. So do you have any other classes of topological full groups for which you hope to have a similar statement?
No. So this is an excellent question. Thanks. And there is a sort of immediate generalization, which is topological full groups associated to one-sided shifts of finite type. The Higman-Thompson group is behind the full shift over D letters, and you can look at shift finite type, but one-sided, and you have a similar class of groups. It works for that. Otherwise, no, and it's a super interesting question. We use some specific properties of the dynamics of the actions of these groups to deduce the theorem from the main one.
Okay, thanks.
Other questions? On the chat, Samuel, is there some questions? So, can there be the actions that are highly transitive? Ville answered no.
I didn't understand, sorry.
Are there the actions that are highly transitive?
No, sorry, I should have, no, of course. Every Z action is just like either the action on Z on itself or the action on a cycle, so it's never highly transitive. But I should have mentioned among the sort of obvious abstractions is, of course, abelian groups are never highly transitive. And actually, also solvable groups. Every group satisfying a law is not highly does not admit any highly transitive action. So even solvable groups don't, for instance.
Okay. So if there are no other questions, let us thank again Nicolas